Welcome back. In this video I'm going to talk about statistical power and statistical errors, which are two important concepts to think about when we are interpreting the results of inferential statistical tests and when we are actually designing quantitative research. So firstly, what are errors? They're very much linked to how we do inferential statistics. So the basic question we're trying to ask is, are some features we observe in our sample, some differences in means, some relationships between variables, a difference in proportions, are they actually reliable indications for something that might be going on in the broader population? And quite specifically, we're asking how likely would it be that we observe the data that we have observed if the null hypothesis was true, so if there was no actual difference, relationship, whatever it might be in the population. Now, unsurprisingly, error occurs when our decision about the null hypothesis doesn't match reality. And it's not an error in the sense of us having done anything wrong. It's just inevitably what happens when we are relying on probabilistic methods. Sometimes we're right, sometimes we are wrong. But it's worth thinking about how to design our inquiry in a way that makes sure that we are not wrong too often. So this question whether our statistical test results match reality can, I think, be approached quite well for a practical example. So let's think about a fire alarm that indicates, ideally, whether or not our house is on fire. So we have four possible states. The fire alarm might be on or off, and the house might be on fire or not. Sometimes that's something probably all of us have experienced. The alarm goes off, the house is not on fire, it's a false alarm, it's clearly an error. Quite often the alarm doesn't go off and the house is not on fire. That's the standard situation, not an error. That's when we rightly believe that the house is not on fire based on our fire alarm. The most problematic situation clearly is when the house is on fire and the fire alarm indicates that it's not. Another type of error, different type of error, but also error. And obviously, ideally, if there's a fire, the fire alarm should go off and save the day. We can now translate the situation into the language of statistical null hypothesis significance testing. So we always have a state of the world. In the world, by definition, the null hypothesis is true or false, but we don't know it, which is why we're doing inferential research. In terms of the research we're doing, we run some kind of statistical test, and that test gives us license to either reject the null hypothesis or to retain it, to fail to reject it. So again, we have a decision criterion, we have a state of the world, and we have four possible outcomes. They now have just specific terms, but their interpretation is quite similar to the case of the fire. So we might reject the null hypothesis, we might call fire when there's in fact no fire. It's called the type 1 error, it's a false positive. That's the one we've already talked about. It's what we determine by setting an alpha level. So if we say we set an alpha level of 0.05, then we accept that in 5% of the cases when we test a false hypothesis, so when the null hypothesis is in fact true, we will reject it, we will publish or conclude to a false positive. Clearly we can also be right, the null hypothesis can be true, nothing is going on, and our test indicates nothing is going on, so we don't reject it. When the null hypothesis is false, and in fact something is going on, we can again make an error if our test indicates that nothing is going on and we fail to reject the null hypothesis. And the final possibility is to correctly reject it, which is of course ideally where we want to be, because ideally we want to put forward a research hypothesis that's true, and then get data that allows us to reject the null hypothesis. So how can we balance those four boxes? First one is the type 1 error rate, the alpha level. And that's just based directly on the output of a statistical test. Any test tells us how likely we would have been to see data, such as the data we have observed, if the null hypothesis was true out there in the world. And then we need to decide how we want to interpret that probability, because that determines how many type 1 errors we commit and how often we correctly accept that nothing is going on. So we need to make a decision, and we need a criterion for the decision. And the way we set up that criterion determines exactly how often we make type 1 errors. Usually we set it at 5%. The reason why we don't set it at 0%, it would be nice to make no type 1 errors, to have no false positives in our literature. The reason why we don't do it is because it conversely affects the type 2 error rate. If we never want to be wrong, then we just have to be very cautious, and we will never make any positive statements. We will never accept research hypotheses. So the alpha level determines how many false positives we make, how many errors we make on that side, but it also determines how much evidence we need to accept a research hypothesis. And if we need a huge amount of evidence, if we have a very strict alpha criterion, then we will have a lot more false negatives. We will often say we don't have enough evidence to reject the null hypothesis when we in fact should reject it. But then better, the type 2 error rate is also determined by how much evidence we actually have. So it's balance between how much evidence we need and how much evidence we have. And to try to get more evidence, there are a couple of things that will help us. So if we're researching something where there's a large effect, and we observe a large effect, clearly gives us more evidence than if we observe a small effect is quite likely to arise due to chance, a large effect much less likely so. Related to that is the idea of a signal to noise ratio. If I have lots of noise in my data, I have less evidence, so that's something to possibly control for in the data collection. And a larger sample size helps. Because again, a larger sample size leads to less variation, leads to a smaller sampling error. So the type 2 error rate is determined indeed by the type 1 error rate. If we're very strict, we will make more mistakes on this other side. But it's also determined by features of our research, like those three. So the converse of the type 2 error rate is what we call statistical power. So that's the power to find an effect if there really is an effect. And it's quite important to think about it before conducting a study, because if we conduct a study, it's very unlikely to find an effect if there is one. Then that study is just uninformative, because if we don't find an effect, we don't know if that tells us anything about reality or just confirms what we should have known about our study design. In the sense, that's unethical to spend resources, involve people in pointless research. And it's certainly just not a good idea, since researchers are constrained. So there's a common expectation that's pushed more and more by funders in particular, that studies should only be run if they have a power of 0.8. So if there's an 80% chance to find an effect, if there really is an effect. And that chance of finding the effect, the power, is determined by a couple of different factors. It's quite importantly determined by the effect size, and that's the standardized effect size. So the standardized effect size also takes the variation of it into account. So we need a large and consistent effect to have high power, ideally. Clearly we don't know that in advance, since that's also the main research outcome. So it's important to estimate the effect size based on the literature. So we might say, well, we're now researching this effect in British PhD students. We have some literature from American undergraduate students that gives us a sense of the effect size. So let's use that as an estimate. But it's quite important to be conservative there, because it's also becoming clearer and clearer that the published effect sizes tend to be quite a lot higher than what you find in replication for various reasons. So to estimate power, we need to decide on an effect size. Second factor is the study design, and there primarily the question of whether we have a repeated measures design, where one participant or one case contributes multiple data points, or an independent samples design, where each participant only contributes one data point, there's less control, there's lower power. And then the third aspect is the sample size. A larger sample makes it more likely to find an effect, if there really is one. So these are kind of three ways to think about maximizing power. At this point, it's also helpful to think about whether that always makes sense. There's this nice quote saying, a difference in order to be a difference must make a difference. Maybe there's no point in running very highly powered studies to find very tiny effects. So sometimes it's also about thinking, what's the minimum effect size there should be in the world for my results to be interesting? Set your effect size to that and accept that there might well be some effect, but it's not an interesting effect, and that's why you fail to find it. But how do we actually determine power? So we talked about the factors that influence it, but how can we get this 80% number? One way to get to power from these parameters is to simulate lots of samples and then test whether the association that we expect is significant. And the share of significant results is exactly what power is about. So if this we simulate running our study many times, power indicates how likely we are to find the result. So if we then run it many times, the share of successes should correspond to the likelihood of success. For many common tests, it's easier to get power. We don't need to run complicated simulations, but we can just use functions that calculate the power. In R, the power package, PWR package, is very helpful for that. And such functions generally allow us to solve for one unknown. So we can use them to calculate power based on effect size and sample size, for example. But we can also use them, more importantly, to calculate sample size, given the level of power that we want and the effect size that we expect. Because that's the way to try to make sure that we're running studies that are adequately powered. Let's look at an example of a teaching intervention. And in fact, something that would be interesting to study with this course, namely the question of whether a flipped classroom approach makes the core quantitative methods course more effective. So the first question would be, what kind of effect size can we expect? There's little research on that particular question, so we might decide to just look at education interventions in general, and there in fact effect sizes are usually quite small. So if we say it's quite a large intervention, so it should have a bigger effect than some small educational interventions, we might say, well, we expect 0.2 standard deviations difference between a flipped classroom and a traditional teaching style. In a recent meta-analysis looking at lots of different effect sizes in educational interventions, that would already be kind of at the upper end. So let's assume that for now. We need to decide on a design. A very easy way would be to do it between participants, have some students take it in a flipped classroom approach, other students in a traditional lecture approach, compare the two means. So if we now want to run this in the recommended way and have 80% power to find an effect if there is one, how many participants do we need? Let's use the power package in R. We just need to give it the parameters that we already have. And then we get this result. And it shows us that we now should in fact have these 393 participants in each group. So in total, almost 800 participants for our simple experiment. Do we really need that many? Well, we can simulate it for verification, so we can go the other way around. Here I'm basically simulating 500 samples under the null hypothesis, when there is no difference, 500 samples under the research hypothesis when there's a difference of 0.2 standard deviations. And then I'm calculating all the p-values for these 500 samples and then seeing in what share of situations the p-values are smaller than 0.05. And in a particular run, of course, every time you run it, you get a different number, since these are randomly generated numbers. By the time I run it, I got to 82% power. So these two results clearly go together. We would need about 800 participants to run a meaningful study into this question. Unless we expect that the effect size is a lot larger, but we have little reason to expect that based on the literature. So what could we do to reduce the sample size? Well, we could ask the question a bit differently, say, does flipped classroom and traditional lecturing, does it have a different effect in a couple of courses? And then we could do it with repeated measures. In that case, we could now take a group of students and randomly assign them in 2 different classes to either experience a flipped classroom teaching style or traditional teaching style, making sure that each student experiences one class of each, and then we could compare the results in those 2 classes. So we could still assume the same effect size. How many participants do we need now? We know that a repeated measures design gives us higher power, but how much is the difference? Can again use the power package, just need to add that we're now looking for a paired t-test as the design. We get the results, and this time we just need 198 pairs. Since each participant provides 2 data points, each participant is a pair. So rather than 800, we now need 200 participants. We can again simulate this to verify, and this time we have a very specific null hypothesis here. The null hypothesis is that the average of the differences between the 2 classes among the students, that the average there is equal to 0. So I'm running this one sample t-test, getting the p-values, and again this confirms that we are at about 80% power. So this is an example for how to calculate power and also for how powerful repeated measures designs can be. If they work, you need many, many fewer participants. So what to remember from this video? First point is this importance of really thinking about type 1 and type 2 errors and of power, with the aim to find ways to avoid both type 1 and type 2 errors, and actually design research that is likely to yield reliable conclusions. Just one more example for how to think about that might be the criminal justice system. So again, we have an indicator, a jury decision, they decide either guilty or not guilty, and we have a state of the world where the defendant is, in fact, either innocent or guilty. Type 1 error would be equivalent to false convictions here, which certainly sometimes occur in the case where the defendant is innocent, or hopefully in more cases, the jury arrives at a not guilty verdict, and that's a success. On the other hand, in the case where the defendant is guilty, we might get a false acquittal, or again, we might get a success. Very clearly, one way to deal with these errors is to trade them off against each other. So we can make sure never to convict an innocent person by just not convicting anyone. However, that clearly leads to lots of false acquittals. Conversely, we can make sure never to have false acquittals by convicting everyone. That leads to lots of false convictions. So one thing is, how do we trade those 2 off? In general, we tend to have very clear standards there. In criminal justice, we say, well, the thing that matters most is that we only convict people who are guilty beyond reasonable doubts. So let's keep false convictions down. In statistics we say we don't like false positives because they make the whole literature quite shaky, make it difficult to have solid foundations. So let's keep the type 1 error rate very low. But if we have fixed that, then we need to think about how to move in the other column between successes and false acquittals. In the criminal justice system, obviously that means having good prosecutions, having resources there. Very similarly, in our area of quantitative research, it means actually designing good research that is highly powered to deliver meaningful results. Okay, what else to remember apart from this first point? Well, clearly low-powered research, while it's unfortunately common, is quite futile and often doesn't produce interesting results. And when we talk about open science and replicable science, we'll talk about some additional issues that come along with this, like the fact that a lot of low-powered research isn't publishable unless you find exciting results, and thereby leads to quite a big distortion in the published literature. You need to remember that power is determined by effect size, sample size, and the research design, and that we try to choose a combination of those three to achieve 80% power. Why 80% rather than 100%? Well, again, because there's a balance between investments and the chances of success. We don't always want to run huge, very expensive samples just to move from 80% success rate to a slightly higher success rate. There are ways to calculate power in R, most notably the power package, PWR package, and they should be used to decide on a sample size before starting on your own study, and of course can be used to look at published studies and figure out whether they were adequately powered. We'll do some of that in class, so I look forward to seeing you there.